Welcome back. In this video, we're going to be talking about annuities. So in our last video, we introduced the time value of money. We looked at simple interest, continuous interest, and compound interest. So in this video, we're going to continue looking at compound interest, but what we're going to do is we're going to add in regular payments. So let's take a look at the two different types of annuities we're going to be looking at. So first of all, an annuity is an account into which equal regular payments are made. So what I mean by equal regular payments, that is, it's the same payment every time, and then also with some regular frequency. So if you have a savings account that you put $100 a month into that account, that's an equal payment if it's $100 every month, and then it's regular because it's every month. And so that would make that account an annuity. So an annuity could be an account that you pay money into or an account that you take money out of, like a retirement account. But anyway, they're just accounts that have equal regular payments. So the two types of annuities we're going to be looking at are ordinary annuities, where payments are made at the end of the period, and then annuities due, where payments are made at the beginning of the period. So the second type, the annuity due, we won't have as many of those, but on the TVM solver on the calculator, let's go ahead and just pull that up. If we go to Apps, Finance, and then TVM solver, down at the very bottom, there is a payment field that says end or begin. We're always going to assume it's end unless specified otherwise. So if it says annuity due, then we change that payment from end to begin. Or if it says payments are made at the beginning of the period. That's a little bit more obvious, but we also have to look out for annuity due. So again, it's not just the word annuity. We don't change it to begin every time we see annuity, only specifically for annuity due. All right. So those are the two types of annuities we're going to look at. Let's look at some examples. All right, $200 is deposited each month into an account earning 2.3% annual interest compounded monthly. We want to know how much will the account contain in 3 years. All right, so let's get our calculator out. We're also going to solve later on for the contributions and the interest. All right, so N is going to be the number of times interest is compounded, which is also going to be the same as the number of payments. So $200 is deposited each month for 3 years. So each month for 3 years, that's 3 times 12 for the amount of compoundings or the amount of payments. So we can actually just do that calculation right in here. It's 36, which we can just type in, or we can do 3 times 12. So there will be 36 payments, and interest will be compounded 36 times. Our interest rate is 2.3%. We're not given a present value, so we'll assume that it is 0. Payment. All right, so it's payment because it is deposited each month. So it is an equal amount every month. So it's equal and it's regular. It's got a certain frequency. So we're going to put that in to our TVM solver. Now, the $200 is a deposit. So that is money moving away from the person into the bank. So that means that is going to be a negative $200. So remember that when money is coming to you, it's positive. When it's moving away from you, it's negative. So even though it's going into your bank account or whoever's bank account this is, it's still negative because it's like you're loaning the bank money. All right. So then our future value is going to be positive. So the idea is we are giving up $200 a month now to get some amount of money later on. All right, it is deposited monthly, so our payments per year and compounds per year should both be 12. That was listed there as 12 from the last problem I did. So we'll just keep that there. And then now we just want to solve for the future value. So we'll press alpha and then enter. And we see that we get 7,446.83. So 7,446.83. I think that's what that was. 7,446.83. Yes. All right. So that's how much the account would contain in 3 years. All right, the next two pieces of information we want are what are the contributions and what is the interest. So contributions is how much did this person put into the account. So they put in $200 each month for 3 years. So we can calculate that pretty easily. So $200 times 12 times per year, so that's monthly, times 3 years. So it would be $7,200. So contributions is essentially if you just kept that money. So rather than putting it into a bank where it earns interest, if you just put the $200 into a box every month for 3 years, you would have $7,200. So the reason there's more than $7,200 is because of the interest that is paid by the bank. And the interest is just the difference between those two numbers. So the bank, you can take out of the bank $7,446.83, but you only put in $7,200. And so the difference of those two things is the interest, which would be $246.83. So there is no complicated calculation for interest. We don't use simple interest or anything like that. Interest is just the difference between what did you put into the bank and what were you able to take out of the bank at the end. And we'll look at this again in terms of loans here in a little bit. But let's go ahead and look at another example. All right, so for this example, an account contains $1,000. If quarterly payments of $500 are made into the account, how much will the account contain in 5 years if it earns 1.4% annual interest compounded quarterly? All right, now, so before we do this one, let's distinguish between a present value and a payment, because these are kind of easily confused. So the account contains $1,000. That's going to be the present value. So the present value is a one-time deposit or just what the account contains at the very start. A payment is something that happens with some regular occurring frequency, so they're equal regular deposits or withdrawals, more than one of them. So if it's just a one-time thing, it's a payment. But if it's more than once, it is a payment. All right. So let's go ahead and work this problem now that we know that. All right, so an account contains $1,000. All right, so let's go to our TVM solver. And let's zero out the first 5 fields. Always a good idea to do this so you don't accidentally keep in some numbers from last time. All right, so let's start with N. So quarterly payments are made into the account for 5 years. So quarterly payments, that's 4 per year. And for 5 years, so 4 times 5, that gives us 20 payments, or 20 times the interest is compounded. The interest rate is 1.4%. The present value, that's how much the account starts with, and that is $1,000. Now, it says the account contains $1,000. That is not any different than someone deposits $1,000 into the account to start off. So it's negative $1,000 either way. The timing does not matter. So it could already contain $1,000, or we could put $1,000 in it. It's negative either way because it's moving from the person to the bank. All right, the payments, that's that regularly occurring deposit. That's $500. And that is also money going into the bank. So that is a negative number as well. Now, there are some problems in this unit where you can get away with not knowing where the negatives go. But there are a number of problems where you really, really need to know which numbers are negative and which numbers are positive. So don't just get into the habit of saying, well, some of them work even if I put the negative in the wrong place. Make sure you know where the negatives go, because on problems like this, or lots of other problems, including most of the problems on the finance project, you will need to know where the negatives go. So the present value and the payment here are both negative because both of those are money that is going into the bank. All right, so interest is compounded quarterly, so we'll change our payments per year and compounds per year to 4 because payments are made 4 times a year and interest is compounded 4 times per year. All right, so then we want to solve for the future value. So we'll press alpha and then enter. And we'll get $11,411.96. So $11,411.96. Yeah, 96 cents. All right. So after 5 years, we get $11,411.96. All right, so now we want to find the contributions. So the contributions is all money put into the account. So that's going to be the original $1,000 plus the quarterly payments of $500. So we need to account for both of those. So the contributions, we'll add in the $1,000 plus quarterly payments of $500. So that's $500 times 4 times per year times 5 years. So that is $10,000. So we can see that our contributions are $11,000. Again, interest is just the difference between what was put into the account and what was taken out of the account. So you can put in $11,000, you can take out $11,411.96. So $11,411.96 minus $11,000. And that's going to give us interest of $411.96. So that would be the amount of interest that is earned over those 5 years. All right. So that's how payments work in annuities. The next type of annuity we're going to look at is a loan. So loans, we need to know a couple things about loans. So first of all, a down payment. So a down payment is an amount paid up front on a loan. So for example, if you want to buy a $25,000 car and you don't have any money you want to spend on it right now, you would need a loan of $25,000. However, if you wanted to buy a car for $25,000 and you had $5,000 that you could pay for it right now, then you only need a $20,000 loan. So the $5,000 would be your down payment. You're going to pay for part of it up front, and then you get a loan for the remaining balance. So that's what a down payment is. You pay for part of it up front and get a loan to cover the rest of it. All right, so then the present value is always the loan amount. So the present value is not the purchase price, because the purchase price is really irrelevant, because however much you spend on something is not how much your loan is for necessarily. So to find the loan amount, we would take the purchase price and subtract out the down payment. So in my example, if you bought a car for $25,000, you paid $5,000 up front, we would do $25,000 minus $5,000, and you would get the loan amount is $20,000. So you would get $20,000 from the bank, you would have $5,000 of your own money, and you can use that to buy a $25,000 car. All right, the future value of every loan, at least in this class, is going to be 0. And that's typical of basically every loan. The idea being, how much do you want to owe after you've made all of your payments? Well, $0. You want to pay off the loan. So the future value of a loan is going to be $0. And then a term you're going to see is amortize. So amortize means to pay off with equal payments. And that's what we're going to be doing with the TVM solver. The TVM solver can solve for the amortized payment, which means what is the payment that you need to make each time period to pay off the loan so that you get to $0 with the last payment. All right. So now that we know all that, let's look at an example. Sam is purchasing a house for $250,000 with a 5% down payment and a 30-year mortgage at 4.3% interest. What is the monthly payment necessary to amortize the loan? In other words, what is the monthly payment necessary to pay off the loan over those 30 years. And then we want to answer a second question: how much interest is paid over those 30 years? All right, so we need to figure out a couple things. So first of all, he's purchasing the house for $250,000, but he's putting 5% down. So that means he doesn't need a loan for $250,000. So first step, let's find out how much of a loan he needs. So $250,000 times 5%, 0.05, means Sam is going to pay $12,500 up front. So that's how much he's going to pay up front, and then he'll finance the rest with the mortgage. So $250,000 minus $12,500. So remember, purchase price minus any down payment gives us the loan amount. So $237,500 would be the loan amount. All right, so now let's go to our TVM solver. Let's zero out the first 5 fields. All right, so Sam is making monthly payments. That's 12 per year for 30 years, so times 30, so that's 360 payments. The interest rate on his loan, 4.3%. The present value, that was the loan amount. So we figured out the loan amount was not $250,000, but $237,500. All right, the payment, that's what we're trying to figure out. Future value, that's 0 because he wants to pay off the house in 30 years. And then he's making monthly payments. So payments per year and compounds per year are both 12. All right, so we can solve for our payment. Press alpha and then enter. We get $1,175.32. $1,175.32. So that's the monthly payment necessary. The interest paid would be the difference between how much money Sam was given by the bank and how much money Sam gives back to the bank. So Sam is going to give $1,175.32 each month for 30 years. So times 360. So that's the total amount of money that Sam would give to the bank. So we can calculate that real quick. So $1,175.32 times 360 payments. So that's going to be $423,115.20. So that's how much Sam would have given to the bank. Now, what we want to subtract out of that is not how much he paid for the house, so not that number, but rather the amount that he got a loan from the bank for. So the amount of money that the bank gave to him. And if you remember, that was the loan amount, or the purchase price, $250,000, minus the $12,500 down payment. And so that was $237,500. So we're going to take the $423,115.20. That's how much Sam gave to the bank, and we're going to subtract out the amount of money that that the bank gave to Sam in the first place. And so that would be $185,615.20. So almost $200,000 in interest over those 30 years. So that may seem like a lot, and it is. It's a lot of money. But the idea is that it is over 30 years. So generally, houses appreciate in value, at least over that long of a time period. So while you do pay a lot of money in interest, houses are frequently a good investment. But it is always a good idea, if you buy a house, to pay a little bit extra on your loan. If Sam, for example, paid $1,200 a month on his loan instead of $1,175.32, he'd save himself a lot of interest. So anyway, that's how mortgages work, and that's how loans in general work. So You may have noticed here, there is nothing in this problem that says compounded. And that is true. Loans are not compounded. So the interest, every month, interest is charged, but then it's also paid off that same month. So in our next video, we're going to look at an amortization schedule where we see that money is charged every month, but also paid off that month. So interest doesn't actually ever compound. So loans are the one type of problem, or really anything with a payment, we're going to be able to use the TVM solver for, even though interest isn't compounded. So if you have regular payments, you're going to be able to use the TVM solver even if interest is not compounded. All right, let's look at one more example. So loans are one type of annuity where the balance decreases over time. So with a loan, you start off owing a lot of money and then you make payments and you pay it off over time. There are other types of accounts where you start with a large balance and that goes down. A retirement account is one of those. There's other types of accounts as well. Another example, which you will see a similar example in the homework, is the lottery. So the winner of a lottery can choose between 29 annual payments summing to $1.6 billion or a lump sum payout of $950 million. What interest rate does this assume? So this is actually how the lottery works. So I forget how long ago this was, but this was the record lottery jackpot at the time. And so I looked up the rules on it so that I could make this example. So the payout, or the jackpot, was $1.6 billion. You could take out $950 million and take that as your payment, or you could take the $1.6 billion paid out over 29 years with one payment per year. So the reason for that is because when a state or whoever runs the lottery, whenever they say there's a $1.6 billion jackpot, they don't actually have $1.6 billion on hand. In fact, what they have on hand is $950 million. But they're assuming they can invest that $950 million at some interest rate that would pay out $1.6 billion over those 29 years. So we want to figure out what that interest rate is. All right, so let's go to our TVM solver. All right, so apps, finance, TVM solver. All right, let's zero out the first 5. All right, so N would be the number of payments. So the way this will work is if you choose the $1.6 billion, then you're paid out one payment a year for 29 years. So that is 29 payments. All right, the present value, that's how much it is worth right now. That's the amount of money they have right now, and that's $950 million. So that's 950, 0, 0, 0, 0, 0, 0. It's a whole lot of zeros. $950 million. All right, let's skip over payment for right now. The future value is going to be 0 because they're going to pay this out to you if you won the lottery, which we just finished a unit on probability, so you probably know you're not going to win the lottery. But anyway, if you were to win the lottery, they would pay out this money until they owed you nothing else. So future value would be 0. It's annual payments, so payments per year, compounds per year are 1. All right, so the payment is the next thing we need to figure out. So the payment is how much money they would give you every year for 29 years. Well, they're taking $1.6 billion and they're splitting it up over those 29 years. So $1.6 billion, that's $1.6 billion. It's a whole lot of zeros, divided by 29. And we can actually just do this calculation right in the TVM solver. So we're taking $1.6 billion and we're dividing it by the 29 payments to see how much money that would be every year. And so that would be, let's see, about $55 million, a little over $55 million per year. So you can choose either between $55 million a year for 29 years or $950 million all at the same time. So now what we want to do is find the interest rate. And to do that, we'll go up to interest rate and press, let's see, Did I have my negatives right here? We got to think about that. Let's see. The present value is $950,000. And then the payment, that should actually be negative because that is the amount that they would pay out. So we're kind of pretending that we are the lottery here. So if they have $950 million, they're going to pay out that. So let's put in a negative sign there. You could also pretend that you're doing it from your perspective, in which case those signs would be switched. So negative $950 million and then a positive $55 million. But either way, we need a negative sign on one of them. So again, the way I chose to do it was from the whoever's handling the lottery. But the switch would be doing it from your perspective. Anyway, we'll get the same answer either way. All right, so let's go ahead and solve for this. So what we get is 3.88% interest. So what that means is that $950 million today is worth the same amount as $1.6 billion paid out over 29 years at 3.88% interest. So that's what the present value of something is. The present value is how much something is worth right now. So that's why if you buy a house, if you didn't have a down payment, that would be how much that house is worth right now. So the present value of the lottery is they're saying it's worth $950 million right now or $1.6 billion over the 29 years. So the idea here is that those are the same amount of money. The amount of money now, $950 million, is worth the same as $1.6 billion over 29 years if we assume an interest rate of 3.88. All right. Well, that's it for today. In our next video, we'll continue talking about loans and interest, and we'll look at amortization schedules. So that's it for this one. I'll see you next time.